Yeah, I'm Alberto Fernandez, and today I'm gonna talk about a library that I've developed. So a little bit about me. I'm a software engineer from Barcelona. I did JavaScript on a previous developer life and discovered Clojure on 2018, looking for languages more close to the mental model of data transformation and list processing and stream processing and all the functional constructs that are so natural in Clojure. So I worked out on the market for 3.5 years doing full Clojure, mostly on data engineering and moving data around databases, but also backend or frontend if it was needed. And I also do algorithmic trading for fun and experiment. So it's a bit of my pet project where I allow myself to infinitely refactor stuff until I like what I get or until I can play around with enough things. So, and that is what I'm gonna talk about today, because this library was specifically because I needed it for algorithmic trading, but I think that it could be useful maybe in other contexts. So yeah, why I needed this? So I wanted to build these time series indicators that are so fancy, and you see them sometimes with all these candlestick bars. So I wanted to get them to work on real time. So in real time, you're only modifying the latest candle, but you still need to keep track of some time in the past, because you might want to do some statistic with the 10 previous values or 20 previous values or things like that. So they are incremental computations. So you introduce a new timestamp, but they keep their own value and they keep incrementing each other, they themselves. And some of those indicators depend on other time series. So you will see that sometimes these indicators are a combination of other upstream indicators. So we're gonna see just a few formulas about them to get started. So the one on the left is a bit easier. It's just a mean, so it's just an average. But here you see the K. So the K is like the timestamp, because at a specific timestamp, the moving average at a specific timestamp is the previous K values. So the previous period values. So the moving average at K, which is the timestamp, is the summatory of all the values divided by the period. So it's normal average, but at a specific point in time. And then the one on the right is called the MACD, or moving average convergence, divergence. And here you see what I was talking about, combining them together. So to get the MACD, so the MACD on itself is 3 indicators, it's not just one. So you have the MACD, the signal of the MACD, and the histogram of the MACD. Sorry about the typo, histogram, it's histogram. And they depend, so the MACD depends on 2 other moving averages with 2 different periods. So how can we do this in Clojure? So just Clojure. So I'm gonna walk through a bit of the code that you might do initially to build this. So first of all, we can code the mean, which you reduce summing all the values. So this is not a moving average, it's just the mean. So for any values, and you divide by the count. Then you have another function. It accumulates a time series. A time series, you can think of it as a sorted map. I use sorted maps for them. So basically, you assure, so the keys are the timestamps, the values is the specific value that that time series have. So accumulating a time series is a very simple computation. You just you're associating into the map, and then you have the moving average. So to do the moving average, you have your accumulated value. So it's something you have to keep track, and we'll see later, because for each one of them, you have their own state that you need to pass to themselves all the time. And you have the source of the time series that you want to do the moving average. You have a period, which is how many timestamps you want to go loop back to have the mean. And then the timestamp. So in this case, it tells you increment my actual state of the moving average using this source with this period at this specific timestamp. So to get the values that you need for the mean, for the average, this is not really important. It's just some sorted maps that you do a subseg until you arrive at your timestamp. You get the value and you take the latest of them. Just think of it as the tail of your the tail of your source up until your timestamp that you want to calculate in here. And then if you have enough values, because moving averages, they start having values after you have at least period numbers on your source. So if that happens, then we can associate on the timestamp the mean of our tail. Okay. And this is another one we'll see later. Actually, I think I have it. No, okay. So let's see just another computation. And this is the one that we will need for the MACD. We have it here. So we have a time series that is a subtraction from one to another. So we'll do that as well. You have your values, source A, source B. So you have a time series that is A minus B at this specific timestamp. You get both their values. When they both exist, you associate that onto your accumulated value. So yeah, this, let's say you want to build the chart we saw before with only the moving average. So you got your sorted map for your source, you got your sorted map for your moving average, and then you have the period. And then, so a function that might keep incrementing a moving average. So this could be a function that you would call on an atom. Sorry, this is an atom. So you calculate your new source, which is accumulate time series of your source with new timestamp and new value. Your new moving average is your moving average with the actual value, new source, the period, and the timestamp. And then you return a new value for the atom that keeps accumulating value. So if we start executing this, sorry, what's that? Accumulate time series. Okay. I didn't execute, load all the file. So, okay, so now put 1, you put timestamp 2, timestamp 3, and now you see that the moving averages start accumulating values. Timestamp 4 after the source, so because you have your period there of 3. So okay, so far it doesn't look too bad. Let's go for the MACD now, which is the one that starts to have intermediary values. So when you want to create the value for a new MACD, you already have to create all your sorted maps here, and you need to know what the values are so what the structure of the values is of these moving averages. So and you see Now we need a function just to create the value of what a MACD is, and then we need another function to process the MACD itself, because its value is a bit more complex. It has 5 different time series and things like that. But yeah, still we can do new fast moving average. So we do a moving average of the accumulated value that we have here. We have the slow moving average. We have the new MACD, new signal, new histogram. So you see, we call the moving average, where each of the values are the ones that we are keeping track here. The subtract. And then we return again the new value of the MACD. And then if we go to have a chart for that, it looks really similar to the above. You accumulate your time series and you process your MACD. So if we do this here, timestamp 1, timestamp 2, timestamp 3, timestamp 4. So this one, now the MACD is accumulating values. Timestamp 5. Now the signal and the histogram are timestamp 6. So, okay, so we have kind of solved what we wanted, but there are some things that didn't like, or that I think that make it difficult to create more complex things, because this MACD is still on the not very complex side of formulas. So there are other indicators that are even more complex than that. So the first thing is that the state and the process are in different places. So you have your new state of the MACD on one side, and you have the process on the other side, and you have to know where everything is, and you have to take care to link every value to the new function that is being returned, to the new function that will increment that specific value. And you need to do that in order. So you need to also keep track of the ordering that you need, because you need to calculate the fast moving average before the MACD. Otherwise, you wouldn't have incremented that. So, as I put here, so the process is responsible to connect the incremental values to the functions that need to date them, and use the correct order of dependencies. And you need to know the format. So imagine that, and because this happens, there are moving averages that are a composition of another moving averages. So now the state of that moving average is no longer a sorted map. It's something that you don't know what it is, because each kind of moving average might create its own intermediary states. So you start to not know how things are. So, and then you could still work it this way, but now you need options here of what function are you gonna call to create your moving average. And then the process needs to also know what moving average do you want to use to pass its a specific value. So what I wanted to, so yeah, it's difficult to compose steps because each intermediary value might be, so if you want to allow customization, for instance, of the internal moving averages, and they are composed, now you are coupled to the internal and intermediary structure that they might have, and in which keyword they might return you the value and things like that. So also, if you wanted to parallelize this, because this is something that is highly parallelizable. So if you have 8 indicators, they can be parallelized, and even the intermediary nodes, they could be parallelized as well, but how do you opt in at any level of that? You could only opt for that parallelism on the top level, but maybe you have one indicator that has complex 20 intermediary nodes somewhere. So how would you parallelize those or opt to parallelize those without forcing the parallelization on the user? So what I wanted is to be able to compose these different elements of the indicator and these different time series that they're all just other time series that need to be combined in a way that is more similar to the formula, and especially where I don't need to keep track of the internal values or the specific schema that each node has. And ideally, so a bit of the mock-up of what I would like to do is something, so if I have a fast-moving average and a slow-moving average, I want to be able to create the MACD as in I create a fast-moving average, a slow-moving average, a MACD, a signal, a histogram, and I just return the ones you want. So I think that ideally, what I wanted to look for is a way where the state of each of these computations and the function that accumulates this value was somehow together, so that there's not this separation of my whole intermediary steps and my sequential process where I need to know what needs to be calculated first, in what order, what depends on what, while I'm processing it, and things like that. So that's where I started to look for something that could help me to join those two things together, the state and the computation that returns the incremental state as a node, as something that was joined together. So then, so what I started to do is to see that there's a graph here. So there's a dependency graph. So your fast-moving average and your slow-moving average, they both depend on the source, the incremental source, that just increments new values. So, and the MACD depends on both the fast-moving average and the slow-moving average. Then your signal depends on the MACD, and the histogram depends on both the MACD and the signal. So with this graph in mind, can we create each of these in a way that are on their own data structure, instead of having to recreate on your mind this dependency graph every time that you need to calculate something? So that's when you actually build this graph, and the different kinds of nodes of this graph are input nodes and compute nodes. So the input nodes, they just allow new data to flow into the graph, but they are not incremental and they don't keep the value. They're just a way to send new data through that graph. And then your compute nodes is something that combines a state and the function that keeps incrementing that state, but, and we'll see later, in a way that still remains pure and immutable. So how does this look on Graphcom? Is for your input, you call G input node, and for the compute nodes, you call compute node. You send a map of dependencies that can be any type of nodes, either input or either other compute nodes. And then the function that computes the new value receives as first parameter the incremental value of that node on a certain execution context. And the second argument is a map that has the same keys as your sources, but now those keys don't have the node, they have the value of the node. So now you can code a pure function that just computes your incremental value given the pure, the values of each of the nodes. And this function doesn't need to care about nodes or Graphcom or whatever. You could abstract outside, test it, how good you do with any Clojure function. And then you create a graph and you specify labels for your nodes. And one of the important parts here is that when you define the graph, you don't need to label every node. So you could only label the nodes that you want to get the value after that, and the inputs where you will need to send new data. So one thing that you can do is on the sources, you can create inline a new graph. And that graph doesn't need to have a value. It's something that is internal for another graph. And this is something that we will see later when we try again with the MACD. So, but this is just a specification so far. This just tells me I have an input, I have a compute that depends on my input, and I have a graph where I'm interested on my input and my compute, but this doesn't process anything. This doesn't have any kind of value or anything like that. So now it's when we process the graph, and we need two new concepts. One is the processor, which compiles and executes the graph. It could do some kind of topological sort and have a data structure that would be useful for it to be able to know in which order all the nodes of the graph are computed. And then there's the context. The context is your whole immutable graph with the incremental values and the processors and the processor compilations. So every time you modify this context, either because you add new processor compilations or either because you are processing your graph with new values and getting new incremental values, this context is immutable. So you can reuse, you can access previous states. There's no atom anywhere. What you would actually do is put your context in an atom, and then, as we've done before, just with your map of indicators, now it's just this context that you keep processing. And this looks like this. You call context, you build your graph, and then you pass a processor. There's two of them currently, sequential and parallel. You can omit the second argument. It will use by default the sequential processor. And yeah, as you see, you can call process. You send a new value for an input node. That returns the context as well, so you can keep processing it. And when you call gvalues, it returns a map of all the nodes that you have labeled and not everything that is internal and you might not be interested on it. And yes, you can see here it has incremented 1 and 2. So yeah, now let's go back to the MACD and see how it could look like now with Graphcom. So remember, I wanted something like this. So with Graphcom, when I use this, I will add a sum on the beginning to tell you that this returns nodes. So we have our accumulate time series. So right now, because they return nodes, so first thing is that we have already removed an argument from all of our functions. Now you don't need to pass the current state. Now you only need to say what's my source, what's my dependency, what node is gonna give me the values I need. And then you specify, and then we can actually call the functions as we coded before. So here, new data will be a vector key value of timestamp and whatever value. So apply accumulate time series. The first time you execute, the accumulated value is nil. So that's why we have our OR that if it doesn't exist, we do a sorted map, new data. Moving average, it looks mostly the same. We just call, we tell it new data because we want to know what new timestamps exist. But we also depend on the source now, which will be something that might be an accumulated time series or might be another time series, wherever it comes from. So the same new data source, we call the function above, we send the source, the period, and the first new data, which is the timestamp. We're not interested in the value in the moving average. And the subtract node, more of the same. We just call subtract. We have source A, source B. We subtract A from B. And now our MACD, which is a function that returns the nodes that compute the MACD. And it only returns the ones we're interested in, which are the MACD, the signal, and the histogram. We don't want the fast moving average or the slow moving average. They're just some intermediary values that we need for our other values. So we can just keep composing nodes this way. And now, so the MACD is going to be a subtract node, which takes another node, which in this case will be a moving average node, another moving average node. Our signal will be a moving average node of our MACD node returned by this, and the histogram will be the subtract node of the MACD and the signal. So with these kind of functions, we're not processing anything. We're not caring about what's the state, where's the state. It gets passed to you as a function. And when you get to the point where your formula is just a combination of other nodes, then you don't even create a compute node. You don't even code any function. You're just combining them together and just returning more nodes. So now let's define an execution context. We'll put that in an atom. This will create our chart. We have a new data. This is where we will send our new timestamps. We have our source that accumulates time series. And this time we're going to add a moving average of period 2 and a MACD of periods 2, 3, and 4. So 2 is the fast, the slow, and the signal period. And in our graph, we're gonna, so this returns a map of nodes, not just a node. So now we can do new data source, moving average, and histogram. And we'll take the histogram for the MACD. So at this point, when I'm defining my MACD or my graph here, I don't even know how many intermediary nodes there are, and I don't want to know. I just know that the MACD returns me these nodes. Imagine that we could have a moving average that instead of being this simple moving average, would be an indicator that has 3 or 4 intermediary more values. It could be very easy to change because this function, as long as you return me the time series value of your computed value, you no longer care of how many intermediary or how many nested values you need to have in the middle, because I'm just only interested on your value. And what Graphcom does is that it will recursively add all the nodes that are not labeled to the graph. So as long as you label some downstream node that you're interested in, everything that goes above that and all the dependencies, all the tree of dependencies from there up until the top are added recursively. So they will be computed even if you don't even know that they're there. You create, and then we create the context. Here, we're gonna use the default processor and put it in an atom. and then we will swap process and start in just one, and we will read the values that are stored inside our context. So we start by one, we see how our source is accumulating things. Our moving average histograms not yet, because we still need more values so that they start producing things. So we keep producing things, we keep adding new timestamps, we keep adding new data, and we start to see how they start to build up. Now that I have enough timestamps that I have introduced, now my moving average, my histogram, they start to build up, and we could keep going and going. And this was a more simple example. So it's something a bit more complex. You could have some mechanisms so that you can limit your amount of timestamps that you want to keep. Let's say 30, 40, 50. So you would have something that also removes the ones that are in the top, things like that. But from here, we basically achieved what I wanted, which is that when I'm composing a formula for this kind of indicators, I no longer care about the values. I no longer care about the order, no longer care about where everything is stored, where intermediary values is stored, and things like that. So when these indicators become very complex, and when the formulas become to be quite big, and even when you want to combine these big ones between each other, this allows for more simplicity. So yeah, it just helps me keep my sanity when I'm trying to build those formulas. So yeah, I built this basically to build tacos, which is the collection of time series indicators. They're mostly for trading, so you can check it out as well. Basically, it's a collection of time series indicators that return Graphcom nodes, usually either one node or a tuple of nodes. And then you put them in your graph, you combine your graph, and yeah, you can start pushing new values. And I'm gonna go quickly just over one of the extension points that Graphcom has, which is the processor protocol. So a processor, there are two currently, which are the sequential processor and the parallel processor. And you can build more, so to adapt to your specific work, or how much work each node has and things like that. You might want other kinds of parallels, different threads. I use pmap on the parallel, so it's quite dummy. It uses just pmap, but you could do some kind of queuing and things like that. So there's two functions, the compile and the process. And basically the process receives the compilation returned by compile. So compile is create a data structure to traverse the graph, starting from a specific input set, so a set of inputs. And that compilation will be used on process. And the thing is that you can create different traversal methods depending on your input. So now imagine that you have two different time frames together where you want to do indicators for each time frame and then join them somehow downstream. So now you have two inputs. So the current processors, what they do is that they will only process the part of the graph that would be affected by the input that has new values, because maybe you don't have new values for both of the inputs all the time. So you optimize that by only computing all the nodes that are depending on that root input node that has new data. So so the other ones are not even executed. So just a quick look for the compilations. You see here, I've used the MACD for now, but if you see that they're basically a topological sort. So each node is processed before each node is processed only when their dependencies have been already processed. And if you see the parallel one, the fast moving average and the slow moving average, you remember that they were together, so they don't depend on each other. So those two can be calculated in parallel and then join them on the MACD when you need to subtract the fast minus the slow. Other, because you can create something else. So for instance, if PMAP is not a good parallelism for you because it will spawn a new future per each node, maybe you can create something more complex and say, okay, I have 2 CPUs, so I will divide all my parallel nodes into sets, compile them in parallel. So you can do some mixture between parallel and sequential and things like that. So here, this is my reason for leaving open this extension point is to be able to experiment with the performance for specific graphs and topologies and things like that. So, okay, a bit of areas of improvement that I think they're worth looking at. So the error handling is currently a bit of a pain point because if it throws an exception, you don't know which node threw the exception. You just have an exception there. So I think that one of the things that I can do to solve that is to grab the exceptions in an xinfo, and I would like to build some kind of path from a labeled node to the intermediary node that failed, so that when you're observing a failure, you can see, okay, my histogram that depends on my MACD, that depends on my fast moving average, and the fast moving average through an exception. So you can easily detect which node, even if it's intermediary, which node actually failed to be able to fix it. So this is something I would like to get done because I think it's something that currently it's a bit of a pain point. And two more things is graph visualization and tooling around the data file to be able to navigate the graph. I haven't experimented a lot with this, but I think it's something that is nice to have. And also performance, it's always something that if can be improved, yeah, it's good to have as well. Yeah, that's it. So you have both of the links here. You can find me at Vortex on GitHub and Clojurians. Yeah, thank you for being here. And now if there are any questions.